Hello. This notebook is a fast paced tour through 10 years of breakthroughs in natural language processing. We started in 2013 with Word2Vec and end with ChatGPT and alignment. Each chapter builds on the last, and by the end, you'll understand how language models went from predicting the next word to having full conversations. So let's get into it. We have 5 chapters here: the basics, sequential models, transformers, large language models, and human alignment. This is the roadmap of evolution of NLP, the prerequisite setups and stalls. Standard setup, PyTorch is our deep learning framework throughout. Hugging Face Transformer is imported for the BERT and GPT sections later. If it is not installed, the notebook falls back to pseudocode examples. The basics of language modeling. Before a model sees text, we have to convert words into numbers, that is tokenization. There are 3 main approaches. Word level is simple, each word is one token, but the vocabulary gets huge and unknown words crash the system. Character level fixes that only 26-ish characters, but sequences becomes extremely long and lose word meaning. Subword Subword tokenization used by GPT and BERT strikes the balance. Common words stay whole, rare words split into pieces. This is how modern LLM handle text. Moving ahead to tokenization. You can see the output here, the character level tokenization and word level tokenization, then subword level tokenization. Simple tokenizer, we built a tokenizer from zero fit, the function fit here. This scans the text and assign an integer to every unique word. Encode encode function converts a sentence to a list of integers. Decode reverses it. This is exactly what early NLP systems did. The limitations is obvious. If a word was not in the training vocabulary, it gets an unknown token and all information is lost. You can see the key inside the vocabulary trade-off. Models like GPT and BERT use subword tokenization. Moving ahead to word embedding. Word embedding are the breakthrough that changed NLP. Instead of treating each word as an isolated symbol, we map it to a point in a high dimensional space. Words with similar meanings end up near each other. Here we initialize embeddings randomly. In practice, they are learned from billions of words using Word2Vec and GloVe. The class word embedding is shown here. Word embeddings created, sample embedding for king. Word similarities. This heat map shows which words are similar to which. Notice the king and queen are hot. The king and queen. They have higher similarity, while king and cat are quite low, suggesting that their relationships are not programmed, they emerge from training on text. The geometry of the embedding space encodes semantic meaning. Moving ahead to word analogy, this is the famous result from the Word2Vec paper that shocked the NLP world. If you take the vector of king, subtract man, and add women, you land close to queen. The embedding space is not just grouping similar words, it is encoding relational structure. The direction from men to women represents gender. The direction from a country to its capital is another. This showed that language has geometric structure. King is to man as women is to queen. Moving ahead, 2D visualization. We project hundreds of dimensions down to 2 so we can see the structure visually. Words cluster by category, royalty words together, geography words together, animal is in their own groups. This spatial organization come entirely from patterns in text with no human labeling. The word embedding chart. Moving ahead to sequential models. Simple RNN from scratch. An RNN processes a sequence one step at a time, passing a hidden state forward. At each step, it combines the current input with the previous hidden state using a weight matrix and a tan-H activation. The hidden state is the model's memory. It carries context from earlier in the sequence. The problem on long sequences is that the memory fades. Gradient from early tokens vanish as they are multiplied through dozens of steps. This is our simple RNN. It has forward pass, visualize, processing. Moving ahead, we have LSTMs. The LSTM adds three gates to control information flow. The forget gate decides what to erase from memory. Values near 1 keep information, near 0 erase it. The input gate decides what new information to write. The output gate decide what to expose from the cell state. This explicit gating mechanism lets gradients flow over hundreds of steps without vanishing, which is why LSTMs dominated NLP from 2014 to 2017. This is the simple LSTM we have created. Moving ahead to LSTM versus GRU comparison. Seg-to-seg visualization. By 2014, researchers combined two RNNs, an encoder and a decoder. To build translation systems, the encoder reads the input sentence and compresses it into a single fixed size context vector. The decoder then generates the output sentence word by word, conditioned on that vector. The bottleneck problem, a single vector must capture everything about a long sentence. That is where attention comes in. Moving, this is the sequence to sequence graph. Moving ahead to attention mechanism. The problem with seg2seg was the encoder must compress the entire input into a single context vector. This is like trying to summarize a whole book in one sentence and important details get lost. The solution is attention. Attention, introduced in 2015, solved the bottleneck. Instead of compressing everything into one vector, the decoder can look back at every encoder state and decide how much to attend to each word. Here, weight 0.72 at position 1 means the decoder is mostly looking at the second word when generating this output token. This dynamic focus is the core intuition behind all model transformers. Moving ahead to chapter 3 Transformers. In 2017, Attention is All You Need introduced the transformer, which uses self attention instead of recurrence. Every token creates three vectors: a query vector, a key vector, and a value vector. The query vector suggests what am I looking for, a key vector suggests what do I contain, and a value vector suggests what information do I carry. Each token computes attention scores against every other token by comparing its query to its value, to their keys, and the result is a weighted sum of all values. Every token sees the whole sequence at once and not just what an RNN has passed forward. The self-attention formula given here, it's the softmax of q k to the power t upon dimension of keys. This is the self-attention class. It has a forward pass, visualization. Moving ahead, we have multi-head attention. One attention head learns one type of relationship. Multi-head attention runs several in parallel. Here, 8 heads. Each head projects into a lower dimensional space, computes attention independently, and the results are concatenated. Different heads specialize. Some track syntax, some handle long range dependencies, some focus on local context. This is why transformers are so expensive. Moving to positional encodings. Unlike RNNs, the transformer processes all tokens simultaneously. It has no built-in sense of order. Positional encoding fixed this by adding a unique signal to each position. They use sine and cosine waves at different frequencies. Position 0 gets one pattern, position 1 gets a slightly different pattern, and so on. The model learns to use these patterns to reconstruct word order. Next, we have complete transformer architecture. Putting it together, input tokens get embeddings plus positional encodings, then pass through a stack of encoder blocks, each with multi-head self-attention, a feed-forward network, residual connections, and layer normalization. The decoder is similar but also has cross-attention to attend to the encoder output. This full architecture underlies BERT, GPT, and every major language model since 2017. Moving to chapter 4, large language models. GPT is a decoder only transformer trained autoregressively. It predicts the next token given all previous tokens. To enforce this, we apply a causal mask. Each position can only attend to itself and earlier positions. The upper triangle of the attention matrix is set to negative. Yeah. Is set to negative infinitely before softmax, making those weights 0. This is how GPT generates text one token at a time. Next, we have BERT architecture. While GPT reads left to right, BERT uses bidirectional attention. Every token attends to every other token simultaneously. BERT is a pre-trained with masked language modeling. Randomly mask 15% of tokens and predict them from context in both directions. It does not generate text, but its representations are extraordinarily powerful for tasks like classification, question answering, and named entity recognition. Alignment and ChatGPT, the human alignment, where we make AI useful and safe. Large language models have a fundamental problem. They generate plausible sounding text, not necessarily true text. When the model does not know something, it often makes something up confidently. That is called hallucination. A model trained to predict the next word has learned to sound coherent, not to be truthful. Solving this required a new training approach, reinforcement learning from human feedback, RLHF, and Instruct GPT. Reinforcement learning from human feedback is the secret behind ChatGPT's helpfulness. Step 1 is fine-tune GPT-3 on human-written examples of good behavior, supervised fine-tuning. Step 2 is train a reward model that scores responses based on human preferences. Step 3, use PPO, a reinforcement learning algorithm, to optimize the language model to maximize that reward score. The result is a model that learned not just to predict text, but to be helpful, harmless, and honest. This was all about this notebook. In just 10 years, NLP went from manually engineered feature to systems that pass the bar exam. The thorough line is clear: better representations of language, bigger model, more data, and finally, learning from human feedback to align behavior with human values. Every step built directly on the previous one. This is the architecture that led to large language models being used today. Thank you for being here in the video.